Thanks for joining me today. I'm Ilya, Senior Solutions Engineer with 6+ years of experience at several small and large companies such as Oracle, Binance, and Fireblocks, focusing on improving businesses with innovative AI, cloud, and SaaS solutions. Today, I'll be focusing on a mission critical observability case study using Grafana for an aerospace and advanced manufacturing company called Otto Aviation. Otto Aviation is building the Phantom 3500, a revolutionary jet designed around laminar flow aerodynamics to slash fuel consumption by over 50% and also lower emissions by 90%. Over this presentation, I'll show you how Grafana's scalable enterprise ready platform can harmonize computational fluid dynamics, manufacturing, test, and flight telemetry streams, delivering actionable insights, forecasted anomalies, and integrated dashboards to power digital twins and streamline engineering processes. I'll also go over an architectural implementation of the technologies as well as a proof of concept demo highlighting solutions for the various challenges that engineers at Otto Aviation are encountering. Today, you'll be sitting in as my client, Otto Aviation, looking for new technologies to transform their processes as well as the aviation industry. One of the biggest challenges in modern aerospace industry is the gap between the as designed aircraft and the as operated reality. Today, I'll walk you through an architectural blueprint for closing that gap, giving you a unified view from the factory floor to the fleet. The content will go over some of the Otto's vision, some of the challenges that currently are present, some of the problems, then principles, pillars, some of the components are an architecture that I propose, the architectures, and we'll close with an actual proof of concept live demo. Before I dive in, I want to make sure that we're all aligned. I see that Otto is a company that is poised to transform aviation. The focus on aircraft zero and test like you fly philosophies, which were proven and championed by Scott Bell, is a clear indicator of sophisticated systems level approach to engineering. I also understand your ambition to create a true digital twin and your core need for a central integrator to unify your tool chain from manufacturing to computational fluid dynamic outputs and flight telemetry, as well as preventing teams from getting overwhelmed by data. Let's start with major headwinds auto aviation is facing today. First up, data silos. You've got CFD outputs, flight telemetry, Dassault records, and vehicle health data all in different places. It's a real pain for engineers to access and correlate. Next, tool fatigue. Your team is manually stitching dashboards together across various systems such as MES and PLM. They're not software developers, they need plug and play tooling. Third, sheer volume. High frequency sensors, big CFD files, real time hardware data. It's a lot to handle. Finally, there's no unified digital twin in place. You can't represent the factory, the aircraft lifecycle, or the as maintained fleet in one system yet. Let's also talk about strategy and infrastructure needs. You follow a test like you fly philosophy, meaning you need traceability between simulation and real telemetry, alongside comparative analysis across flight campaigns. With build versus buy, custom development is slow and expensive. You're after pre built, low touch solutions so teams can focus on innovation rather than integration. And because test stands and planes operate offline sometimes, you need a hybrid deployment model that works at the edge and syncs back via Starlink or LAN whenever the connectivity returns. To meet these challenges, I propose a unified observability platform. This wouldn't be just another tool, it would be a foundational layer for the entire engineering, development, and operations processes. These are the five key principles that I propose and I believe that are necessary to address your main challenges and guide our architectural implementation. First of all, we need a single source of truth, a centralized hub to unify all of the data sources. We need a proven and scalable data foundation, a robust backend to handle massive data loads from testing, real time, and simulation. We need to be able to integrate all of the existing tools with a full scale tool chain integration. We need to enable the test like you fly digital twins that will allow real time streaming and visualizations for most of the critical use cases. And lastly, we need a flexible and secure deployment model within the whole system, a hybrid model for on aircraft and on premises systems with security in mind. Here are some of the larger technical components that we'll be using in this implementation. Grafana is a multi-platform open source analytics and interactive visualization web application. It can produce charts, graphs, and alerts. It can be on the web, it can be on cloud, or it can be on hardware and connected to various supported data sources. We'll also use InfluxDB, a time series database developed by the company Influx Data. It will be used for storage and retrieval of time series data in fields such as operation, monitoring, application metrics, Internet of Things sensor data, and real time analytics. We'll also use the plugins and integrations ecosystem that Grafana provides. Grafana has a large marketplace of various plugins that will be able to connect to various different pieces of software that already exists in the implementations that we have within the company. And we'll also use Kafka, an open source distributed event streaming platform that multiple different companies use for high performance data pipelines, streaming analytics, data integration, and mission critical applications. Here I'm going to briefly introduce the components before I really show you how everything fits together. At the heart of our system is the centralized observability hub powered by Grafana. This acts as our single pane of glass, unifying disparate data from engineering, manufacturing, and testing into one place for clear visualization and real time monitoring. To store these vast amounts of information, I'm using a specialized multi-user database. Again, we'll leverage that InfluxDB for high frequency time series data from sensors, since it is designed to ingest these types of data readily. Also, role-based access control will be granted through Grafana, allowing high performance access in secure ways to different teams. Connecting various systems and existing software, we have that plugins marketplace that I have talked about and the integrations layer. This will allow us to pull any data from any system using custom plugins and even standard APIs. The AWS IoT TwinMaker plugin allows the creation of digital twins with operational data overlaid in real time on the Grafana dashboard for that digital twin system we were envisioning. The lifeblood of this system is telemetry and streaming data handled by Apache Kafka. This is a resilient data pipeline that streams high fidelity telemetry from onboard sensors in real time, allowing us to monitor assets as they operate. And finally, the entire architecture a supports a hybrid model of on cloud and on premises systems. Using Grafana, we can collect the data at the edge on the aircraft to make decisions immediately. This data can be securely synchronized to a central instance and allows the opportunity to analyze it further in conjunction with those digital twins that we've created. In essence, this architecture breaks down data silos to provide a comprehensive, real time, and actionable understanding of all of our assets from their inception and designing to their maintenance and functionality. This slide presents my complete end-to-end vision. It's a holistic architecture designed to connect the entire aircraft lifecycle from its digital birth and simulation to its operational life in the field, with Grafana serving as the single pane of glass over it all. On the left is the ground platform, where data from design, manufacturing, and testing is collected using a resilient Kafka bus, which then is passed on to Grafana. On the right, the operational aircraft uses its own onboard Kafka cluster for data durability and a Grafana agent for onboard decision making. The link between them, Starlink, streams the flight data back to the ground for further analysis and evaluation with the ground teams. The true heart of this architecture is Grafana, connecting all of this infrastructure, querying all of the data sources to create the complete digital thread. It's a single platform where our teams will visualize, analyze, and act on information to build and operate smarter aircraft. Let me dive deeper into the architecture in the next few slides. The process here begins on the ground. Data from the test bed is published to a central Kafka bus, which then serves as the resilient ingestion point for all of our data streams and all our test streams. From there, plugins connect data to Grafana directly or persist it into the InfluxDB. That's the database that we're using. This all culminates in Grafana, which acts as that central hub for our engineering teams to visualize system performance, validate hardware and software integration, as well as analyze the test results all in one place. The key evolution here is how we leverage Grafana to deliver deeper insights. Using the digital twin plugin, the Grafana now becomes our correlation engine and something that will help us with visualization of the actual factory floor. It queries not only the real world data from the digital twin factory, but also the as designed test data from our InfluxDB. This empowers the engineers to visually overlay simulation versus reality directly within the central Grafana workspace, providing immediate data driven validation of those models. The process begins on board the aircraft with the sensors generating raw data. This data is immediately published to an onboard Kafka cluster. We use the Kafka here as a highly durable and persistent log for the high frequency data, ensuring that no data is ever lost. Grafana also to Grafana subscribes to this onboard Kafka stream. It can perform initial processing, give insights to onboard teams, and other metrics. A vehicle health monitoring system on the aircraft can help make decisions about maintenance and repair immediately and quickly. On ground, the data from the aircraft is received by our central Kafka bus through Starlink, where it can be joined with other data for analysis. This all comes together in Grafana. It is the platform that creates the digital thread querying data from every stage of the aircraft's lifecycle. It allows teams to trace a component from its manufacturing record through ground testing and into its real world operational life. Again, all from that single unified interface. This overall architecture leverages the complete end to end data pipeline we've established, flowing data reliably from the onboard Kafka cluster at our edge to our central platform. The crucial evolution is that Grafana is no longer just a system for observation, it becomes the engine for insights and action. Using Grafana, alerting and visualization capabilities, we can also identify performance trends, anomalies, and predictive maintenance opportunities across the entire fleet. The insights generated within the platform are fed back into the engineering and design teams, allowing them to improve the digital twin, refine the simulations, and ultimately make the aircraft smarter, more reliable, and actionable. Now I'd like to move into a live demo of the environment. To show you what this looks like in practice, we'll walk through these four scenarios that mirror a day in the life of your engineering teams, addressing your key challenges. The first demo, the aircraft zero dashboard, will start with the core need for integrated systems testing. This dashboard will provide a real time and at a glance situational awareness of live test, mirroring the test like you fly philosophy. The second demo, the digital twin demo, will correlate simulation versus reality. We'll address the need to validate engineering models by directly overlaying CFD simulation data with real world wind tunnel test results and will show a true foundational step in creating a true digital twin. The demo 3, the digital thread manufacturing to maintenance, will demonstrate a full life cycle view by linking an operational anomaly on specific components back to its original manufacturing data, showing the power of this integrated data thread that we have throughout the system. The fourth demo will show a smarter systems with a will show a Smarter system with proactive alerts will show how the platform moves beyond passive visualization to active monitoring, automatically detecting off nominal conditions, and notifying the right people, making the entire system smarter. So we'll get Grafana running. I've got a local instance here. We'll use brew service to start Grafana, and we'll get a local instance running here. We'll go to localhost 3000, log in, and we'll see the dashboards that I've created for these 4 demos. Now, a little bit of background here. I've already set up a lot of the data sources for the dashboards. This will be our first dashboard that I'll go over. But I've actually set up all of the data sources and I've already connected everything. We are able to actually connect various data sources in our data sources tab. Here in this demo, I'll be actually using a number of CSVs to represent the data inputs, but we're actually able to connect live databases that would be updated regularly in real time from various pieces of sensors or various different test beds. Here you can see a couple of examples of data sources that are already connected. This is obviously the Google Sheets that we're able to plug in, and here is the InfluxDB that I've actually used previously that I mentioned in our architecture. The plugins marketplace here is very vast and expansive in the plugins tab, obviously, and allows us to connect all of those different data sources that I mentioned in the past that may exist so that we can pull them in and do those analyses and create the dashboards. We're also able to create users, teams, and service accounts, and we're actually able to limit the various access to the teams. So if you have a team and you only need them to see a certain dashboard, we're actually able to do that in this tab. Alerting will come in handy later. I'll show it to you as a part of the demo. This is the alerting rules tab where I've set up a couple of alerts where I'm actually able to notify the teams if something has gone above, below, whatever the limits are, and set up an alert rule where people would get notified or systems can get notified. In this case, it's actually sending a SMS to my Telegram bot, simulating maybe a maintenance malfunction or a challenge that somebody may have with a particular system and could get notified very readily and quickly. So we'll go to the dashboards and I'll show you that first demo. Here we're looking at a live dashboard for the Aircraft Zero Systems Integration tab. This is designed to give your ground test engineers a single source of truth. As you can see, we're pulling in real-time data from completely different systems. For example, the avionics bus voltage, hydraulic pressure from the fuel pump, the physical position of the flight control actuator, and the state of a specific valve all in one screen. This directly accesses the challenges of data silos. Instead of having to look for maybe some different tools or different pieces of data in various different software, an engineer can now see how a dip in the bus voltage might affect fuel pressure second by second directly looking at this dashboard. This is about unifying real-time data from flight controls, avionics, power systems all into a single dashboard. And so if somebody needs to do some analysis, we can actually zoom in, take a look at what's going on specifically. And we can actually see all of these data pieces all correlate and all change all at the same time. We're actually able to zoom out later then. So a engineer will spend a lot less time and a lot less effort searching for some sort of problem. Now I've only got a few pieces of data here, obviously, but you can imagine thousands and thousands of pieces of data or data streams that need to be simultaneously examined, managed, and processed. So this makes things a lot more easier. Let's go to the second demo here. While it looks very simple, this next view is crucial for de-risking the program early and directly supporting the test like you fly philosophy. Here we're correlating the simulated world with the physical world. On this dashboard, we're pulling data from two different sources. The dotted line represents the predicted structural strain from a computational fluid dynamics or a simulation model, while the solid line is the measured strain from a physical component during a wind tunnel test. The platform allows you to visually overlay these data sets so you can immediately see where the model matches the reality and where it deviates. And this is how we provide the capability for validating simulation accuracy against physical test data in development. Let's go to the third demo. Now we're expanding from a single test to tracking the entire life cycle of a component. This dashboard demonstrates the digital thread in action. At the top, we have the birth record for a specific actuator, serial number A4B7C9, pulled from your PLM system like Dassault. It shows the manufacturing date and that it passed final inspection. At the bottom, we have a live feed of maintenance events from the operational fleet. Here we can see the exact same component has now been flagged as an anomaly while in service. This provides an unbroken history for every critical part from factory to flight. This is how we create a complete digital thread by linking components manufacturing records to live maintenance events. As you can see here, we've got a big series of events, and we can actually click on these various serial numbers and go through and see the specific details. I've also added kind of a digital twin outlay here of the factory where I'm able to actually see the real usage and stock of the various bolts and screws. We're actually able to see the live production status of the aircraft. As you can see, one of them is 100%, one of them is 90%, and so on and so forth. We're actually able to immediately see and detect the anomalies, the inspections, and see everything readily, really quickly, really easily on the factory floor, as well as some of the QC pass-fail rates and that sort of thing. So we're able to see all of the digital twin manufacturing and also the maintenance situations really readily. Again, connecting those databases to this dashboard and having it all in one place where we're able to actually immediately analyze, see, and what's going on all in one shot here. This system, Grafana, allows us to connect different databases. So if you can imagine, a lot of different sources of data coming in here, from the IoT hardware to maybe some finance data, and obviously databases where we've got maintenance records. This unifies all of that all in one view, all in one shot, making things very easy to go through, detect, analyze, and saving lots of cost, saving lots of time, and making sure everything is on schedule. Also, with this, we're able to do a lot of preventive maintenance, seeing what's going on in the fleet, seeing what challenges are happening overall. So now we'll go to the last demo here. The final view shows how we evolve from passive monitoring to creating the data systems that make you smarter. Here, the platform is not only just displaying data, it's actively monitoring. It has automatically already detected a pressure anomaly in the fuel pump based on the data streaming from the live aircraft. So you can see this right here. But this alert is more than just a threshold breach. It represents a deviation from the digital twin's expected performance baseline. The system automatically correlates the pressure spike with a simultaneous valve change, giving the engineers immediate context. as you can see here. This is the ultimate goal, harnessing the remote monitoring architecture to feed the live digital twin, enabling proactive alerts and even possible predictive maintenance. We've got some live data coming in here, and we're able to see those correlations with the changes. We're also able to see that alert here that we've already set it up. The alerts, as I mentioned, come from the alerting rules, and we are able to actually set up with various different incoming sources of data. And if, for example, in that specific example, that demo 4, we have the PSI go over 1200, it actually sends out a alert and contacts the specific individuals. It could be through email, or it could be through a SMS, or it could be anything. You can set up any sort of alerting system to show that specific change, issue, etc. So in this specific one, I actually set it up to send me a alert rule to my Telegram. And as you can see, I've got a Telegram bot over here. This is where we would set it up, and based on that role, we would have some sort of message sent to the specific system. And we're able to actually send an email, or we've got various other systems that we can send to. So maybe it even contacts a maintenance system, for example. So that's how alerting rules work, and we're able to set it up through Grafana. So that's the last demo. Thanks for joining me on this presentation. If you have any questions, comments, or insights about what I have put together, I'm happy to hear them. Please feel free to send me a DM, an email, or contact me through LinkedIn. All my info is in the bio.